Out there, in the silent, unending dark, the universe is singing. It is not a song for human ears, carried on vibrations of air. It is a symphony written in the very structure of existence, a chorus of whispers and shouts in the fabric of space-time itself. For a century we theorized it was there. For a few short years we have finally learned how to listen. And on August 14th, 2019, from a distance so profound it is almost meaningless, some 800 million light-years away, we heard something impossible. It was not a roar or a bang, but a chirp. An elegant rising tone lasting just a few moments, the sound of two cosmic giants locked in a final frantic embrace. But this was no ordinary celestial pairing. This signal, catalogued as GW190814, carried the ghost of an object that should not exist, a spectre from a cosmic graveyard that defies every category we have for the dead things of the universe. It is a signal that has introduced a profound and unsettling anxiety into the heart of astrophysics. It is the story of a cosmic phantom, an entity so perplexing, so defiant of our understanding, that among some who study it, it has earned a chilling, unofficial moniker, the Death Planet, and the terror it inspires is not of destruction, but of ignorance. It is the fear that comes when you stare into the abyss, and the abyss presents you with a riddle you cannot solve, revealing that our maps of the cosmos have a gaping, unknown hole. To comprehend the gravity of this phantom signal, we must first journey back, not just a few years, but an entire century. We must return to a time when the universe was seen as a grand, predictable stage, a clockwork mechanism set in motion by an unseen hand. This was the cosmos of Isaac Newton. Space was an inert, absolute grid, a passive backdrop. Time was a universal river, flowing at the same rate for everyone, everywhere. Gravity was a mysterious force, a spooky action, yet a distance, that reached across the void to pull objects together. It worked. It predicted the orbits of planets with stunning accuracy. It guided cannonballs and charted the tides. For over 200 years, Newton's vision reigned supreme. The universe was orderly, knowable, and ultimately simple. Then came a young patent clerk in Bern, Switzerland. Albert Einstein was not satisfied with this ghostly, instantaneous force. He imagined what it would be like to ride on a beam of light, and in doing so, he shattered the clockwork universe forever. His theory of general relativity, unveiled in 1915, proposed something so audacious, so reality-bending, it still challenges our intuition today. He declared that space and time were not separate, but were woven together into a single, four-dimensional continuum, space-time. And this fabric was not a passive stage. It was an active participant. Imagine a vast, tightly stretched rubber sheet. This is space-time. If you place a bowling ball in the center, the sheet curves, it dimples. This curvature, this warping of the very geometry of reality, is what we perceive as gravity. A smaller marble, rolled nearby, doesn't feel a mysterious pull. Instead, it follows the curve created by the bowling ball, spiraling inwards in what we call an orbit. The Earth is not being pulled by the Sun. It is following the straightest possible path through the curved space-time created by the Sun's immense mass. The force was an illusion. The reality was geometry. This new picture of the cosmos was beautiful, elegant, and deeply strange. But it came with a prophecy, an extraordinary prediction. If massive objects moving through space-time could warp it, then truly cataclysmic events, violent, accelerating masses, should create disturbances in the fabric itself. They should generate waves, ripples of gravitational energy that would propagate outwards at the speed of light. Like the ripples spreading from a stone dropped into a serene pond, these gravitational waves would stretch and squeeze everything in their path. The Earth, the Sun, our own bodies, would be infinitesimally distorted as one of these ethereal messengers from a distant cataclysm washed over us. The effect would be so small, so unimaginably subtle. Einstein himself doubted we could ever build an instrument sensitive enough to detect such a cosmic whisper. For 100 years, this prediction remained one of the last great unverified pillars of his revolutionary theory. It was a ghost story told by theorists, a phantom vibration haunting the equations but absent from the experimental world. Detecting these waves would require a feat of engineering bordering on the miraculous. The challenge is almost impossible to overstate. By the time a gravitational wave from a distant cosmic collision reaches Earth, its power has diluted across unimaginable distances. The stretching and squeezing it produces on our planet is 1,000 times smaller than the nucleus of a single atom. How could humanity possibly measure such a vanishingly small effect? The answer was an instrument of breathtaking scale and precision, the Laser Interferometer Gravitational Wave Observatory, or LIGO. Two identical facilities, one in Louisiana, one in Washington state, built 3,000 kilometers apart to rule out local vibrations. Each one is an enormous L-shaped vacuum chamber, with two arms stretching 4 kilometers into the landscape. Inside these tunnels, a powerful laser is split into two beams, one sent down each arm. They travel to the end, reflect off mirrors polished to atomic perfection, and return to the starting point to be recombined. In the serene, undisturbed state of space-time, the two beams travel an identical distance. When they meet again, they are perfectly out of sync, cancelling each other out so that a detector sees only darkness. This is a state of perfect null, perfect silence. But if a gravitational wave passes through, it changes everything. For a fleeting moment, it will stretch one arm of the detector, while simultaneously squeezing the other. One laser beam now travels a slightly longer path, the other a slightly shorter one. When they return and recombine, they are no longer perfectly out of sync. A tiny flicker of light, a ghostly signal, leaks through to the detector. This flicker is the evidence. This is the sound of space-time ringing. For years, these incredible machines listened in silence. They were plagued by false alarms, by the rumblings of distant trucks, the subtle tremors of earthquakes, the crashing of ocean waves. The quest seemed almost hopeless. Until September 14th, 2015. A clear, unambiguous signal arrived, first at the Louisiana detector and then 7 milliseconds later in Washington. It was a perfect chirp, rising in frequency and amplitude, the textbook signature of two massive black holes, some 30 times the mass of our Sun, spiraling into each other and merging into one in a final violent convulsion. For a fraction of a second, that single event radiated more energy than all the stars in the observable universe combined. It was a shout from 1.3 billion light-years away. Einstein was right. The universe was singing. A new window onto the cosmos had been thrown open. We were no longer just looking at the universe, we were listening to it. Humanity had developed a new sense. With this new sense, we began to map out the most extreme, the most violent and the most mysterious phenomena in existence. We listened to the mergers of black holes, those points of infinite density where the laws of physics break down, cosmic behemoths whose gravity is so immense that not even light can escape their grasp. They are the ultimate stellar corpses, the remnants of the most massive stars which, upon exhausting their nuclear fuel, collapse under their own stupendous weight, punching a hole in the fabric of space-time itself. We also began to hear the death spirals of another class of cosmic dead, neutron stars. These are the remnants of stars not quite massive enough to become black holes. When they die in a supernova explosion, their core collapses, but is halted by a bizarre quantum mechanical pressure. Electrons and protons are crushed together to form a sea of neutrons, creating an object of almost unimaginable density. Imagine the entire mass of our Sun, compressed into a sphere no larger than a city like Manhattan. A single teaspoon of neutron star material would weigh billions of tons. They are, in essence, city-sized atomic nuclei, the densest form of observable matter in the universe. So, as our catalogue of gravitational wave events grew, a clear picture began to emerge. We saw mergers of smaller black holes with larger ones. We saw pairs of neutron stars colliding in cosmic explosions that forge most of the heavy elements, like gold and platinum. The universe, it seemed, was divided into two distinct populations of compact stellar remnants. There were the ultra-dense cinders we call neutron stars, and there were the gravitational abysses we call black holes. And between them, there was a curious empty space. Observations, both with telescopes and gravitational wave detectors, pointed to a strange division. The most massive neutron star ever found clocked in at around 2.1 to 2.5 times the mass of our Sun. The lightest black hole ever detected was significantly heavier, at around 5 times the mass of our Sun. In between these two values, from about 2.5 to 5 solar masses, there was nothing, an apparent void. Astrophysicists called it the lower mass gap. It was a sort of cosmic no man's land for dead stars. The theory seemed to explain it. The physics of supernova explosions, the titanic blasts that create these objects, suggested that collapsing stellar cores either had enough mass to overcome everything and form a black hole of at least 5 solar masses, or they didn't, and the explosion would leave behind a neutron star below the 2.5 solar mass limit. There seemed to be no stable outcome in the middle ground. The mass gap was a comfortable, predictable feature of our cosmic landscape. It was a fundamental line in the sand drawn by the laws of physics. And then came the signal from August 14th, 2019. The chirp from GW190814 was at first glance another binary merger. The data streamed in and the computers began their work, deconstructing the wave to determine the nature of its source. The heavier object was easy to identify. Its gravitational influence was immense, its signature clear. It was a black hole, a substantial one, about 23 times the mass of our Sun. A standard, well-behaved resident of the known universe. But its partner, the smaller object that had been devoured in the collision, was the source of a growing sense of disbelief among the research teams. As they refined the calculations, a number came into focus. 2.6. The smaller body had a mass of approximately 2.6 times that of our Sun. That number, 2.6, landed squarely unequivocally in the supposedly empty wasteland of the mass gap. It was an object that, according to our best models, should not be there. It was heavier than any neutron star ever observed. It was lighter than any black hole ever observed. It fit neatly into no category we possessed. This is the source of the terror. It is not the fear of an approaching alien armada or a planet-killer asteroid. It is a far more profound, more intellectual horror. It is the dread that comes from realizing your understanding of the world, built upon decades of painstaking observation and theory, is fundamentally incomplete, perhaps even wrong. Imagine being a biologist who has spent a lifetime classifying all life into mammals, birds, reptiles, and fish, only to one day discover a creature with fur that lays eggs and has a venomous spur, a platypus, an animal that breaks all the established rules. GW190814's mystery object is the platypus of the cosmos. It's a chimera, a monster in the classic sense of the word, a being made of parts that should not belong together. It forces us to confront the unnerving possibility that we don't know the full menagerie of cosmic creatures. The neat lines we've drawn on our celestial maps are provisional, and something has just crawled out of the space marked, "Here be dragons." So the grand investigation began. What was this thing? What is this object that has so thoroughly shaken the foundations of high-energy astrophysics? There are 3 main possibilities, each more exotic than the last, and each with shattering implications for our understanding of the universe. The first, and perhaps most conservative possibility, is that the object was simply the most massive neutron star ever discovered. If this is true, it immediately throws our understanding of matter into complete disarray. The reason we believe there's a mass limit for neutron stars is because of something called the equation of state. This is a set of rules that governs how matter behaves under the most extreme pressures and densities imaginable. Inside a neutron star, matter is squeezed so tightly that our theories about it are pushed to their absolute breaking point. We can't replicate these conditions on Earth. Our most powerful particle accelerators can only create tiny droplets of this super dense material for fleeting fractions of a second. To understand it, we must look to the heavens. Neutron stars are our only cosmic laboratories for this kind of physics. An equation of state tells you how stiff or squishy nuclear matter is. If it's relatively squishy, a neutron star can't support much weight. It would collapse into a black hole at a lower mass. If it's very stiff, it can hold itself up against gravity more effectively, allowing for more massive neutron stars to exist. All our current models suggested a limit around 2.5 solar masses, the existence of a 2. 6 solar mass neutron star would mean that the matter inside it is stiffer, more resistant to collapse than we ever thought possible. This would force physicists to completely rewrite the rulebook for the fundamental behaviour of subatomic particles. It could hint at new, unknown forces or particles at play within the crushing heart of a dead star. It would be like discovering a new law of physics, hidden in the densest corners of the cosmos. The very nature of matter itself would need to be re-evaluated. The second possibility is, in some ways, even more tantalizing. What if the object was, in fact, the lightest black hole ever discovered? This too presents a profound cosmological puzzle. How would such a lightweight black hole form? The standard model of stellar collapse, the supernova process, doesn't seem to produce them. The explosions that create black holes are so violent, and the stars that fuel them are so massive, that they are expected to leave behind remnants much heavier than 5 suns. To create a black hole of just 2.6 solar masses from a dying star would require a completely new, previously unimagined type of supernova. Perhaps a star that fails to explode properly, with most of its material falling back into the core in a failed supernova. Or perhaps it was born not from a single star, but from the collision of 2 smaller neutron stars in a previous merger, an event that created a short-lived, supermassive neutron star that immediately collapsed into a tiny black hole. This would mean that the universe has multiple distinct pathways for creating these gravitational traps. It would tell us that the life and death of stars is far more complex and far more varied than our current narratives allow. It would mean the mass gap isn't a true gap at all, but is instead populated by a stealthy, hidden family of black holes born from processes we are only just beginning to contemplate. The universe would be seeded with a population of small, dark predators that have until now completely escaped our notice. But it is the third category of possibilities that truly pushes us into the realm of science fiction, into a universe of speculative physics that is both thrilling and deeply humbling. What if this object was neither a neutron star nor a black hole? What if it was something else entirely new? Something fundamentally alien? One candidate is a hypothetical object known as a quark star. We know that protons and neutrons, the building blocks of atomic nuclei, are themselves made of even smaller, more fundamental particles called quarks. Under normal conditions, quarks are always bound together in 2s or 3s. They are never seen in isolation. But what happens in the hypercompressed core of a massive neutron star? Some theories suggest that the immense pressure could become so great that the very boundaries between the neutrons dissolve. The entire star could transform into a single, gigantic particle, a massive sphere composed of a free-roaming soup of quarks. This would be a new state of matter, a quarter-gluon plasma, a substance that likely has not existed in the universe in a stable form since the first microseconds after the Big Bang. A quark star would be even smaller and denser than a neutron star. It would be a fossil from the dawn of time, reborn in the heart of a stellar corpse. If GW190814's mystery object was a quark star, it would be the first evidence for the existence of this exotic state of matter. It would confirm theories that have lived only on blackboards for decades and open up a new field of quark astronomy, and the possibilities grow even stranger. There is another far more ancient and mysterious candidate, a primordial black hole. The black holes we are familiar with are stellar in origin. They are born from death. But theory allows for another kind, born not from the death of stars, but from the birth of the universe itself. In the very first second after the Big Bang, the universe was an unbelievably hot, dense and turbulent place. The density of energy and matter was not perfectly uniform. Some regions may have been so incredibly dense, so overpressurized, that they spontaneously collapsed under their own gravity, forming black holes without ever having been a star. These primordial black holes could have a vast range of masses, from the weight of a mountain to many times that of our Sun. They would be composed not of matter that once lived in a star, but of the raw, undiluted fabric of the newborn universe. They are relics of creation, if the two. 6 solar mass object was one of these primordial phantoms. It would be a discovery of monumental significance. These objects are also a leading candidate for dark matter, the mysterious, invisible substance that makes up over 80% of the matter in the universe, whose gravity holds galaxies together. Finding one would be like finding a piece of the cosmic blueprint, a direct link back to the fiery moment of creation itself. We would have captured a ghost from the Big Bang. The tragedy and the beauty of GW190814 is that we will never know for sure. The object, whatever it was, is gone forever. In its final moments, it spiraled into its 23 solar mass companion and was consumed, its unique identity erased as it merged into a new, larger black hole. All we have is the echo of its death scream, a few seconds of data captured by our detectors before it vanished from the universe. We cannot point a telescope at it. We cannot study it further. It was an ephemeral messenger that delivered an impossible riddle and then disappeared into the void. But the message itself has changed everything. It has shattered our comfortable categories and forced us to admit the profound depths of our own ignorance. The Death Planet isn't a physical threat, it's a philosophical one. It reminds us that the cosmos is under no obligation to conform to our expectations or our models. It reveals that our neat and tidy zoo of cosmic objects is missing some of its most fascinating creatures. The mass gap is not an empty desert. It is a dark forest, and we have just heard the footsteps of something moving within it. This single event has electrified the fields of astronomy and physics. It has launched 1,000 new theoretical papers, sparked countless debates, and fueled the urgent drive to build the next generation of gravitational wave detectors. Instruments like the Laser Interferometer Space Antenna, or LISA, which will place detectors in orbit around the Sun, and ground-based observatories like the Cosmic Explorer will be vastly more sensitive. They will be able to listen to the universe with breathtaking fidelity, picking up not just the loud shouts of mergers, but the constant quiet hum of the cosmos. They will map the dark side of the universe in exquisite detail, and they will be hunting for more objects like the enigma of GW190814. They will find them. We now know that these mass gap objects are out there, that one discovery implies the existence of many. We have been introduced to a new class of celestial object, even if we do not yet know its name. The terror this event inspired in researchers is the thrill of discovery in disguise. It's the sublime feeling of standing at the edge of a vast, unknown territory. It is the ultimate reminder that science is not a collection of facts, but a continuous process of questioning, of being proven wrong, and of redrawing our maps in the face of new, confounding evidence. The universe is not just stranger than we imagine, it is stranger than we can imagine. And out there, in the silent, unending dark, it is still singing. And we are, at long last, beginning to learn the words. In a universe painted with the fire of a trillion suns, our story has always been one of light. Light is our clock, our compass, our storyteller. It carries tales of ancient galaxies across impossible voids, whispers the chemical secrets of distant nebulae, and paints the faces of the worlds we thought we knew. We have come to expect a certain celestial grandeur, a cosmic artistry in the way planets present themselves. You have seen them in your mind's eye, a gallery of heavenly bodies, each with its own signature, its own way of dancing with the light. Picture the furious churning eye of Jupiter, a hurricane larger than our entire Earth, its bands of ammonia clouds swirling in brilliant shades of ochre cream and violent red. This is a world that shouts its presence, a chaotic masterpiece reflecting the sun's distant rays with bombastic confidence. Its canvas is one of dynamic perpetual motion, a gas giant that wears its turbulent heart on its sleeve for all the solar system to see. We can imagine the ethereal grace of Saturn, a planet so beautiful it feels like a cosmic dream. Its rings, a breathtaking filigree of ice and dust, catch the sunlight and scatter it into a shimmering silver halo. They're a celestial wonder, a billion tiny mirrors creating a spectacle of such delicate magnificence that they have captured our imaginations for centuries. This is a world defined by its brilliant reflective elegance, a jewel box spinning in the silent black theatre of space. Consider Mars, the rusty jewel of our neighbourhood, whose iron-rich dust gives it that distinctive bloody hue. It is a world of stark raw beauty, its canyons and polar caps telling a story of a past that might have mirrored our own. Even in its current desolate state, Mars reflects light with a personality, a character that speaks of geological history and untold stories buried just beneath its crimson soil. And then there is the singular, irreplaceable Earth, our home, a fragile blue marble suspended in the darkness. From space it is a living beacon, a testament to light's power to nurture. The deep sapphire of its oceans, the swirling white patterns of its clouds, the vibrant greens of its continents, all of this is reflected starlight. Our world is a celebration of light, a planet whose very essence is interwoven with the energy it receives and returns to the cosmos. It is the standard by which we judge all other worlds. For decades, this was our paradigm. We believed planets were fundamentally reflective bodies, each one a unique mirror angled toward its star. We built our theories, our models, our very understanding of planetary science on this foundation of reflected glory. When we began to look beyond our sun to the flickering stars in the deep night, we carried this expectation with us. We developed methods of breathtaking ingenuity to find these new extrasolar worlds. We learned to watch for the almost imperceptible wobble of a star tugged by the gravity of an unseen companion. We learned to read the impossibly faint dimming of a star's light as a planet passed in front of it, a transit, a fleeting shadow play staged across light years of empty space. This transit method, our primary window into these alien solar systems, gave us the ability to measure a planet's size and its orbit. But it also offered something more profound, something we were just beginning to comprehend. By analysing the starlight that passed through a planet's atmosphere, or by measuring the total light of the system before, during and after a planet disappeared behind its star, we could calculate a world's albedo, its reflectivity. We could ask the most basic question of all: how bright is it? We found worlds that shone with the brilliance of fresh snow, their thick clouds, bouncing nearly all of their stars' light back into space. We discovered planets that likely had the dull sheen of our own moon, rocky and barren. We even found some that were darker, perhaps the colour of worn asphalt, absorbing a significant portion of their incoming energy. Each discovery added a new swatch of colour, a new texture to our growing tapestry of known worlds. We were filling in the cosmic catalogue, and it was beautiful, varied and exciting. It all made a certain kind of sense. But science, in its relentless pursuit of truth, has a habit of finding the loose thread, the one anomaly that threatens to unravel everything we thought we knew. In the faint, unassuming light of a star hundreds of light years away, astronomers found something that did not fit. They detected a ghost, a whisper. A transit so subtle, so strange that at first it was dismissed as an error in the data, a phantom in the machine. A world was there, a massive gas giant, a hot Jupiter, orbiting its star in a blisteringly fast, terrifyingly close embrace. The data was undeniable. But when they tried to measure its brightness, its reflectivity, they were met with something that bordered on the impossible. The calculations came back again and again, each time confirming a result that defied planetary physics. The number was so low it felt like a mistake. It felt wrong. This planet, this colossal giant larger than Jupiter itself, was not just dark. It was not just dim. It was a world that seemed to be actively consuming light. It was a celestial object of almost perfect, absolute blackness. Imagine charcoal, one of the darkest substances we know on Earth. It reflects about 4% of the light that hits it. The planet they found, this gravitational behemoth, was far, far darker than that. The instruments told a chilling, unbelievable story. This world absorbs more than 99% of the light it receives. 99%. Let that number settle in your mind. It is a figure that pushes the boundaries of our understanding. This is a world that returns almost nothing to the universe. It is a cosmic black hole in miniature, not in gravity but in aspect. It takes and gives nothing back. It is a pitch-black planet. A place so profoundly dark that if you were floating in space beside it, it would be less a visible sphere and more a hole in the starry background, a patch of velvet darkness where a world ought to be. Its only visible signature would be the faint, angry infrared glow of its own internal superheated furnace, a dull cherry-red ember hanging in the void, a fever dream from the deepest, most terrifying parts of the cosmos. You're looking at a monster. Not a monster of fiction, but a monster of physics. A world that breaks the rules. Its existence is a profound and deeply unsettling question mark hanging in the cosmos. How is this possible? What kind of exotic chemistry, what sort of bizarre atmospheric physics could create a planetary surface or an atmospheric shroud that functions as a perfect light trap? In our solar system, dark materials exist, but they are part of a mix. Jupiter has dark bands, but they are contrasted with bright zones. Our moon has darker seas of basalt, but they are set against brighter highlands. Nature as we have always understood it loves variation, it loves contrast. But this world is a monolith of darkness. It suggests uniformity, an overwhelming planet-wide phenomenon that has snuffed out all reflectivity. It has erased its own face from the cosmos. This is not merely the absence of light, this is the active, aggressive annihilation of it. The questions it forces us to ask are fundamental. Does this world have clouds? If so, they are not the water ice clouds of Earth, or the sulfuric acid clouds of Venus, which are brilliantly reflective. They would have to be clouds woven from some exotic, light-devouring substance, a celestial smokescreen of unimaginable scale and efficiency. The proximity of this world to its star only deepens the confounding mystery. It orbits so closely that its year lasts only a handful of Earth days. It is tidally locked one side, perpetually facing the stellar furnace, the other turned forever toward the cold of deep space. The day side, the side we observe, is scorched by temperatures exceeding thousands of degrees, Celsius hotter than the melting point of steel. This is a celestial blowtorch of unimaginable intensity. Conventional wisdom would suggest that such a hot planet should glow, reflecting a tremendous amount of light simply from the sheer energy being poured onto it. Yet, it does the exact opposite. It's as if the planet has harnessed this incredible stellar energy for some unknown atmospheric process that as a byproduct creates this perfect, all-consuming darkness. Could its atmosphere be laden with elements like vaporized sodium and potassium, which are known to be fantastic absorbers of light? Could there be some unknown compound, a molecule forged only in the extreme crucible of a hot Jupiter's upper atmosphere, that acts as the ultimate cosmic sunscreen? Or is the answer something even more bizarre, something that will force us to rewrite our textbooks on planetary formation and atmospheric science? The discovery of this pitch-black planet is more than just a new entry in our astronomical catalogues. It is a philosophical challenge. It reminds us that the universe is not obligated to conform to our expectations or our Earth-centric experiences. For every rule we think we have established, the cosmos seems to delight in presenting us with a shocking, beautiful, or in this case terrifying exception. It forces us to confront the reality that we are just at the beginning of our journey of understanding. The comfortable gallery of worlds we once knew, the vibrant gas giants, the rocky red planets, the shimmering ringed jewels, was incomplete. We had been looking at a family portrait and we had failed to notice the silent, somber figure standing in the deepest shadows at the very edge of the frame. This dark world is a sentinel guarding a new frontier of scientific inquiry. It is a puzzle box delivered to us across hundreds of light years, inviting us to look closer, to think deeper, and to dare to imagine the unimaginable. It is a testament to the fact that the most profound secrets of the universe are not always hidden in the brightest explosions or the most brilliant nebulae. Sometimes they are found in the most complete and utter absence of light. They are waiting for us in the dark. Our journey begins now. We will venture into the heart of this enigma. We will deconstruct the fragile light from its parent star, searching for the chemical fingerprints of the molecules that steal its photons. We will build powerful new computer models attempting to simulate the hellish conditions of its atmosphere, a laboratory of extreme heat and pressure that may hold the key. We will travel back in time to the chaotic birth of its solar system, looking for clues in its formation that might have destined it for a life of darkness. We will stand on the precipice of a new kind of planetary science, one that must account for worlds that defy our most basic assumptions about what a planet should be. The quest to understand this pitch-black planet is a quest to understand the full breathtaking scope of what is possible in our universe. It is a story about a world that absorbs the light, a world that has erased its own reflection, and in its profound and unsettling darkness, we may just find a new way to see the cosmos and our own place within it. The void is calling, and it is time to answer. For millennia, the question was a whisper in the soul of philosophy, a heresy on the lips of visionaries. Were there other worlds orbiting other suns, scattered like sand across the infinite shore of the cosmos? For most of human history, this was a query confined to the realm of pure thought, a grand but untestable speculation. The stars were brilliant, unwavering points of light, their secrets locked away by a tyrant of physics distance. The sheer, soul-crushing void that separates us from them made the notion of seeing a planet, a tiny, non-luminous body, seem like an utter fantasy. It was a challenge akin to standing in Los Angeles and trying to spot a single firefly hovering next to the blinding beacon of a lighthouse in Tokyo. The glare of the parent star was an impenetrable curtain of fire, and for centuries that curtain refused to be drawn. Science, it seemed, had reached an impasse, its greatest instruments staring into the abyss, only to be blinded by the very objects they wished to study more closely. We could map the stars, we could measure their heat and their chemistry, but the families of worlds we suspected they harboured remained ghosts, phantoms in the celestial machine. The breakthrough, when it finally arrived, was not one of sight, but of inference. It was a masterpiece of indirect observation, a way to feel a planet's presence without ever laying eyes upon it. Astronomers realised they didn't need to see the firefly, they only needed to watch the lighthouse. They theorised that as a massive planet orbits its star, its own gravity, though minuscule in comparison, would still exert a persistent pull. It would tug gently but rhythmically on its colossal parent. From our distant vantage point on Earth, this would cause the star to perform a subtle, almost imperceptible dance, a tiny repeating wobble. It was a gravitational waltz with an invisible partner. By measuring the light from the star with unprecedented precision, scientists could detect this motion. As the star wobbled slightly towards us, its light waves would be compressed, shifting towards the blue end of the spectrum. As it wobbled away, the waves would be stretched, shifting towards the red. This rhythmic pulse, this Doppler shift, was the telltale heartbeat of an unseen world. In 1995, this revolutionary technique yielded its first spectacular prize. Around a sun-like star, 51, Pegasi astronomers detected a definitive wobble. The data was undeniable. They had discovered a planet, a colossal gas giant locked in a blistering 4-day orbit. It was a hot Jupiter, a class of world no one had predicted, and with its discovery, humanity was suddenly irrevocably no longer alone in its planetary solitude. The floodgates had been thrown open. This initial method, elegant as it was soon found, a powerful companion. Another technique, conceptually simpler, yet technically just as demanding, began to scan the heavens. This was the transit method. It relied not on gravity but on shadow. If a planet's orbit happened to be perfectly aligned with our line of sight, it would periodically pass directly in front of its star. From Earth, this event would register as a tiny, fleeting dip in the star's brightness. It was the equivalent of watching a distant streetlight and noticing it dim ever so slightly for just a moment, because a moth has flown across it 100 miles away. To catch such an infinitesimal eclipse required telescopes of extraordinary sensitivity, capable of measuring changes in starlight of less than 1 part in 10,000. Space-based observatories like the Kepler telescope were launched with this singular, audacious mission to stare unblinking at a single patch of sky containing hundreds of thousands of stars waiting with infinite patience for the telltale dimming that signalled the passage of a world. The data that poured back to Earth was a revelation. It transformed exoplanets from rare hard-won trophies into a galactic menagerie of staggering diversity. Suddenly we were drowning in worlds. There were super-Earths, rocky planets far more massive than our own. There were mini-Neptunes shrouded in thick, dense atmospheres. We found planets orbiting 2 stars at once, living out a perpetual double sunset. We found rogue planets cast out from their home systems to wander the cold, dark, interstellar void alone. We found worlds of diamond, worlds of water, and worlds of unending lava. This Cambrian explosion of planetary discovery began to fill in the blanks of cosmic creation. We started to build a cohesive story, a grand narrative of how solar systems form and evolve. We developed sophisticated models, elegant theories that could explain the churning atmospheres of gas giants, the delicate geochemistry of terrestrial worlds, and the chaotic ballets of their orbits. The universe, while still mysterious, was becoming familiar. We were learning the rules of the game, the fundamental physics and chemistry that governed the birth and life of planets across the galaxy. We were becoming confident, perhaps even arrogant, in our newfound understanding. We believed we had finally glimpsed the master blueprint, and it was then in a quiet, unassuming corner of the constellation Cygnus that we found a world that broke every single rule we had written. The star itself was unexceptional, a yellow dwarf catalogued as Kepler 1b, one of thousands being monitored for the telltale dips in light that betray orbiting companions. And soon enough the data delivered. A regular, predictable dimming revealed the presence of a planet, a massive gas giant, a hot Jupiter, much like the very first exoplanet ever discovered. It was designated TRIS 2b. On paper, it was almost mundane, another entry in a rapidly growing catalogue. Its mass was slightly more than Jupiter's, and it orbited its star at a perilously close distance, completing a full year in less than 2.5 Earth days. Its surface, or what passed for a surface in its turbulent atmosphere, would be a furnace with temperatures soaring to over 1,000 degrees Celsius. All of this was expected. Hot Jupiters were now a familiar beast. Astronomers prepared to conduct the routine follow-up observations to characterize its atmosphere, to measure its temperature more precisely, and crucially, to determine its albedo, the measure of how much light it reflects back into space. This single number is a planet's defining characteristic. Venus, shrouded in hyper-reflective sulfuric acid clouds, has a high albedo, bouncing back about 75% of the sunlight that hits it. Earth reflects about 30%. Even our own Jupiter, with its swirling bands of ammonia ice clouds, reflects more than half the light it receives. The darkest bodies in our own solar system, charcoal-coloured asteroids, or dusty moons, still reflect a few percent. The expectation for TRIS 2b was that it would be dark, certainly. At such extreme temperatures, the reflective clouds of ammonia and water ice that grace our own gas giants couldn't exist. Instead, its atmosphere would likely be laced with vaporized sodium, potassium, and titanium oxide compounds that absorb light rather than scatter it. The models predicted a low albedo, perhaps similar to our moon's, somewhere around 10%. The team of astronomers pointed their instruments at the system, ready to measure the subtle brightening of the total light as the planet orbited its star, moving from its transit phase to its full phase, just like our own moon. By measuring the tiny amount of reflected starlight, they could calculate its reflectivity. The observation window opened. The data began to stream in, and then silence. An unnerving, confusing quiet in the data stream where a signal should have been. The instruments were checked, recalibrated, and aimed again. The results were the same. There was no reflected light. Or rather, the amount of light being reflected was so vanishingly small, so infinitesimally faint that it bordered on the undetectable. It was statistically indistinguishable from zero. The initial reaction was disbelief. It had to be an error, a flaw in the telescope, a miscalculation in the software, some unforeseen interference from the parent star itself. The scientific process is built on skepticism, and an extraordinary claim requires extraordinary evidence. They ran the numbers again and again, poring over every photon, scrutinizing every assumption in their models. But the conclusion held. It was inescapable, and it was utterly baffling. This planet, this supposedly ordinary hot Jupiter, was reflecting less than 1% of the starlight that fell upon it. It was darker than fresh black asphalt. It was darker than the blackest acrylic paint human technology has ever engineered. This wasn't just a dark world. It was a light-swallowing entity of a kind we'd never imagined. The implication sent a shockwave through the astronomical community. It wasn't just an anomaly. It was a paradox. A planet so large and so hot should have an atmosphere that glows from its own internal heat. While it might absorb most visible light, it should radiate brilliantly in the infrared, a celestial ember hanging in space. Yet even its heat signature was strangely muted, as if something was trapping the energy deep within its core. The established laws of atmospheric physics, the very models that had worked so well for hundreds of other discovered worlds, began to buckle under the weight of this single impossible data point. A planet simply should not be this dark. There was no known chemistry, no plausible atmospheric composition that could account for such an extreme, almost perfect absorption of light. It was a cosmic anomaly of the highest order. What kind of bizarre exotic materials could be floating in its atmosphere to create such a profound shroud? What unknown physical process could be operating in this alien furnace that so completely snuffs out the light of its own sun? The object in the Cygnus constellation was no longer just a catalogue number. It had become a profound mystery, a gravitational sinkhole for light itself. It was a hole punched in the fabric of the cosmos, a place where the light checked in but it never checked out. It was not a world, it was a shadow, and in that profound light-swallowing darkness, a new and terrifying chapter in our search for cosmic understanding had just begun. The numbers that returned from the void were not merely surprising, they were an assault on intuition, a statistical impossibility that echoed through the halls of astronomy departments worldwide, a planet that drank the light. A world wrapped in a shroud of such profound blackness that it barely registered as an object at all, betraying its presence only by the recurring shadow it cast. That initial discovery, the raw, unbelievable fact of its existence, had been the thunderclap. Now, in the stunned silence that followed, came the storm of questions, the urgent, almost frantic scramble for an explanation. For scientists, a perfect mystery is both a torment and a treasure, and this world was the most perfect mystery they had encountered in a generation. The first wave of hypotheses crashed against the shores of the known attempts to anchor this anomaly in the familiar. Perhaps some argued the answer wasn't in some exotic atmospheric physics at all, but something far more primal. Perhaps the problem was geological. We began to imagine a surface forged in some planetary cataclysm, a world paved not with rock or sand, but with a substance that acts as a cosmic light trap. You could picture it vast continent-sized plains of obsidian cooled from a global magma ocean, their glassy surfaces reflecting almost nothing back into space. Or maybe something even stranger, a planet-wide deposition of carbon compounds, not unlike graphite or Buckminster Fullerene's materials whose very molecular structure is a cage for photons. A world sculpted from the darkest materials in the universe, a solid body of almost pure light-absorbing carbon. It was a compelling visceral image, a world you could stand on sinking into perpetual twilight under a sky dominated by its blazing tormented star. But for a planet of this size, a gas giant many times the mass of Jupiter, the very concept of a surface becomes fluid, almost meaningless. There is no solid ground to stand on. Instead, there is a descent, a gradual, terrifying journey downwards, through layer after layer of atmosphere, the pressure mounting relentlessly until the gas itself transforms. It thickens into a strange supercritical fluid, a state of matter neither liquid nor gas, before finally under pressures 1,000,000 times greater than Earth's compressing into a core of metallic hydrogen. The darkness, therefore, could not be a simple coating on a solid ball. The culprit had to be found higher up, suspended in the very air of this alien world. The planet's secret was not geological, it was atmospheric. This realization shifted the search into the planet's vast, turbulent skies. The leading theory, a hypothesis born from our understanding of chemistry, under extreme conditions was as simple as it was hellish soot. Imagine an atmosphere so superheated by its proximity to its star, a celestial blowtorch holding it in a perpetual state of combustion, that complex molecules are constantly being shattered and reformed. In this chemical inferno, hydrocarbons, the building blocks of life on Earth, could be baked into vast, choking clouds of fine, dark particulate. We weren't picturing a planet of rock, but a planet of smoke, a sphere of eternal galaxy-sized smog where every gust of wind is a billowing cloud of black carbon, absorbing the starlight with terrifying efficiency. The idea held a certain grim elegance. It explained the darkness with a known substance, and it fit the environment. This world orbits its star in a blisteringly tight embrace, completing a year in just a few Earth days. Its day side is permanently locked facing the stellar furnace with temperatures soaring to thousands of degrees Celsius, hot enough to melt iron, hot enough to vaporize rock. In such an oven, any methane or other hydrocarbons in the upper atmosphere would be pyrolyzed, their hydrogen atoms stripped away, leaving behind a haze of pure black carbon. These microscopic grains of soot, trillions upon trillions of them, would act like a planetary layer of velvet, catching the incoming photons and converting their energy directly into yet more heat, creating a runaway feedback loop of ever-increasing temperature and ever-deepening darkness. This soot world hypothesis became the front-runner, the explanation that felt most plausible. But in science, plausibility is not proof. A feeling is not data. To truly understand this world, we had to move beyond imagination and speculation. We needed to dissect the faint, fleeting whispers of light that did manage to escape it. We needed to perform a cosmic autopsy. To do that, humanity has devised one of the most powerful tools in its arsenal, a technique that allows us to grasp the chemical soul of a world we can never ever visit. It is called transmission spectroscopy, and it is the closest thing we have to magic. The principle is breathtakingly simple in its conception, yet miraculously powerful in its application. As the pitch-black planet passes in front of its star from our perspective, a tiny fraction of the starlight doesn't just get blocked. It filters through the very edge of the planet's atmosphere, a razor-thin sliver of gas at the terminator, the line between day and night. For a few precious hours, that starlight is on a journey, and the planet's atmosphere is its final gatekeeper. Light, you see, is not a monolithic entity. It is a messenger carrying an intricate code, a full spectrum of colours of wavelengths from the deep infrared to the far ultraviolet. And when this light passes through a gas, a remarkable interaction occurs. The atoms and molecules within that gas are picky. They will only absorb light of very specific wavelengths, specific colours that correspond perfectly to their own unique energy levels. An atom of sodium, for example, will pluck a very specific sliver of yellow-orange light from the passing stream. An atom of potassium will steal a specific shade of violet. Water vapour will absorb chunks of the infrared. Every element, every molecule has its own unique unforgeable absorption signature. They leave behind a pattern of dark lines in the star's rainbow, a chemical barcode that spells out their identity. So if we could capture the starlight before the transit, and then capture it again as it grazed the planet's atmosphere, the difference between the two spectra would be the planet's fingerprint. It would be a list of ingredients, a definitive answer to the question, what is this world made of? The task fell to our great eyes in orbit, the Hubble Space Telescope and its powerful successor, the James Webb Space Telescope. These are not mere cameras. They are cosmic time machines and interstellar laboratories capable of capturing and dissecting light that has travelled for hundreds of years to reach us. For astronomers, securing time on these instruments is a fiercely competitive process. Proposals are written, peer-reviewed and defended with the passion of lawyers in a courtroom. To point a multi-billion-dollar observatory at a single star system for days on end is an act of profound scientific faith. The team that won the observation time for this dark world felt the immense weight of that faith. They were hunting for a ghost, and they had been given the world's most sophisticated tools to do it. The wait for the data is an agonizing period of silence. The telescope, a silent, lonely sentinel in the void, executes its commands with cold precision. It stares unblinking as the distant planet begins its transit, a barely perceptible dip in the star's brightness. The instruments on board, cooled to just a few degrees above absolute zero, begin to collect the photons one by one. Each particle of light is a clue, a single letter in a message of cosmic importance. The information streams back to Earth, a torrent of raw numbers that must be meticulously cleaned, calibrated and processed. The noise from the telescope's own electronics must be removed. The interference from our own atmosphere must be accounted for. It is a painstaking process of digital archaeology, sifting through mountains of data to find the faint, delicate signal buried within. Finally, the spectrum resolved onto their screens, the moment of truth. The horizontal axis represented the wavelengths of light, the cosmic rainbow. The vertical axis showed how much light got through. If the atmosphere was transparent, it would be a flat line. But if it contained absorbing elements, there would be deep valleys, sharp downward spikes at the precise wavelengths corresponding to each chemical. The team leaned in, their collective breath held. They were looking for the barcode. They were looking for the chemical signature of the darkness. Their first search was for the telltale signs of the elements that could form dark light-absorbing clouds in the atmospheres of other hot Jupiters. They scanned the specific wavelengths for sodium and potassium. These alkali metals, when in gaseous form, are known to be incredibly effective at absorbing visible light. On other hellish worlds, their presence is screamed across the cosmos in the form of enormous sharp absorption peaks. They are the usual suspects, the first culprits you look for in a case like this. The team focused on the yellow part of the spectrum, the precise home of the sodium signature. They zoomed in expecting to see a deep canyon carved out of the starlight. But there was nothing. The line was flat, frighteningly impossibly flat. There was no deep valley. There was no sharp spike. There was just a faint shallow undulation, a whisper of a signal so weak it was almost lost in the statistical noise. It was as if the planet had no sodium at all or was hiding it with an almost supernatural effectiveness. They checked the potassium lines in the violet. The same result. A barren, featureless landscape where a mountain range of absorption should have been. The first most obvious explanation that the planet was dark because of conventional alkali metal clouds was not just wrong, it was spectacularly wrong. The planet wasn't cooperating. It was actively resisting investigation. A ripple of disbelief and excitement went through the team. This wasn't a simple problem after all. This was something new. They turned their attention to the soot world hypothesis. Unlike sodium or potassium, which create sharp, narrow absorption lines, a haze of carbon soot would behave differently. It wouldn't target specific colours. Instead, it would cast a much broader, more general pall over the entire spectrum. It would create a gentle downward slope with more blue light being scattered and absorbed than red light. This Rayleigh scattering slope is a well-understood phenomenon. Was it there? They pulled back, looking at the entire visible spectrum, and they could see it, sort of. There was a faint slope, a subtle decline towards the blue end of the spectrum. It was a tantalizing clue. The soot hypothesis wasn't dead yet. It could explain some of the general darkness, but it could not on its own explain the sheer overwhelming degree of light absorption. A soot haze alone wasn't enough to create a world this black. And more importantly, it absolutely failed to explain the other shocking feature of the spectrum, the profound lack of any other chemical signals. Where was the water vapour everyone expected to see in the infrared? Where were the signatures of carbon monoxide or methane? All of these molecules have powerful absorption features fingerprints that should have been easily detectable. But the spectrum was a desert. Across vast stretches of the infrared where the chemical richness of a gas giant should have been on full display, there was only a flat, monotonous line. The planet was not just dark, it was mute. It refused to tell us what it was made of. The very technique designed to reveal its secrets was failing. The light that filtered through its atmosphere was returning to us almost completely unaltered, scrubbed clean of any chemical information. It was as if a veil had been drawn across the planet, a barrier that not only absorbs light but also completely masks the composition of the gas beneath it. This was the moment the mystery deepened into something far more profound. We had come seeking answers and had found only a more perfect question. We had systematically tested the most logical explanations, and each one had crumbled in the face of the stark, silent data. This world wasn't just covered in a dark substance like soot, nor was it shrouded in the kind of clouds we understood. It was a spectroscopic ghost. The evidence suggested that something was happening in that atmosphere that was not in our textbooks, a process so efficient and so bizarre that it could swallow nearly every photon of starlight while simultaneously hiding all of its chemical fingerprints from our most powerful instruments. The scientific community was left reeling, facing a puzzle far more complex than a simple dark surface or a smoky sky. The simple models were broken. The standard explanations were insufficient. The planet was a black box in the most literal sense imaginable, its internal workings completely hidden from view. To solve this, we would have to throw away the rulebook. We would need to explore the very frontiers of physics and chemistry to entertain ideas that bordered on science fiction. The heat on this world we began to suspect might be doing something more than just creating soot. It might be tearing the very fabric of matter apart, creating an atmosphere of disassociated atoms and exotic materials that behave in ways we're only just beginning to comprehend. The easy part of the investigation was over. Now we had to venture into the true heart of darkness. But the math refused to surrender its secret. Every model we constructed, every simulation we ran based on a solid light-absorbing surface, eventually crumbled under the weight of its own inconsistencies. We imagined vast cracked plains of pure carbon, like a world-spanning sheet of graphite. We envisioned jagged continents of obsidian volcanic glass, forged in stellar fire so flawlessly black they would swallow the sky. We even considered exotic forms of matter, theoretical materials that could form a crust capable of this incredible feat of light suppression. Yet each hypothesis left a nagging residue of doubt, a faint but persistent signal in the data that just didn't align. The reflected light, the minuscule 1%, that escaped back into the cosmos to tell us its tale, carried a story that contradicted a simple dark geology. It was as if we were trying to understand a symphony by only listening to a single muffled note, a note that hinted at a much grander and stranger composition. The answer, it turned out, wasn't on the ground we couldn't see. It was in the very air we couldn't imagine. The breakthrough came not from a more powerful telescope, but from a more patient one. We needed to stop looking at the planet and start looking through it. The technique is one of the most elegant in the astronomical toolkit transmission, spectroscopy. As this dark world makes its transit, a tiny fraction of its star's light doesn't just get blocked, it filters through the very edge of the planet through its upper atmosphere. For a few precious hours, that envelope of gas becomes a cosmic prism. The light that travels through it carries an imprint, a ghostly fingerprint of the chemicals floating within. Atoms and molecules in an atmosphere are greedy. They absorb specific frequencies of light, specific colours, leaving behind a pattern of dark lines in the spectrum, a barcode that we can read from hundreds of light years away. It is how we have found water vapour on distant worlds, how we have identified methane, and how we search for the telltale signs of biological activity. We were now turning this powerful tool on the darkest world we had ever known, hoping to read the secrets in its twilight fringe. The first results were so baffling, they were initially dismissed as instrumental error. The teams ran the diagnostics again, and again. The instruments were perfectly calibrated. The data was clean. The problem wasn't the equipment, it was our understanding of what a planetary atmosphere could be. Where we expected to see a forest of sharp, distinct absorption lines, the clear signatures of identifiable gases like hydrogen, helium, or water vapour, we saw almost nothing. But it wasn't a clean slate. It was a strange, unsettling smear. The entire spectrum was broadly and profoundly suppressed, as if the light hadn't passed through a thin, transparent gas, but had been forced to fight its way through something thick, complex, and utterly opaque. There were no clear fingerprints, no simple chemical barcodes. Instead, there were vast, shallow valleys in the data where huge swathes of the light spectrum had been quite simply erased. This was not the signature of a normal atmosphere. This was the signature of a photon trap. The revelation crashed through the scientific community with the force of a paradigm shift. We had been blinded by terrestrial bias, by our experience with the relatively clear skies of our own solar system. We assumed the darkness came from the surface below, while the atmosphere was a mere veil. The truth was far more extreme and far more magnificent. The planet isn't dark because it's made of something black. The planet is dark because its sky is the agent of that darkness. Its atmosphere is not a transparent window to the surface. It is an active, insatiable engine designed to capture and suffocate light. The 1% of light we see isn't reflecting off a planetary surface. It's the last, desperate glimmer escaping from the very top of a colossal, world-spanning shadow. We weren't looking at a dark planet. We were looking at a star being consumed by its own child's heir. The mystery of the pitch-black world had transformed into a far deeper, more disturbing question. What kind of sky can literally devour the light? The spectral data, those broad smeared absorptions, held the clues. Such a pattern pointed not to simple gases, but to a chemical cocktail of extraordinary density and complexity, something that could only exist under the most extreme conditions of temperature and pressure. The models began to churn once more, this time fed with this radical new premise. And from the complex mathematics, 3 terrifying and beautiful possibilities emerged, each one painting a picture of a world more alien, than we had ever dared to conceive. The first and perhaps most intuitive hypothesis centered on a sky filled with metallic vapors. Imagine a world so blisteringly hot that rock-forming elements we think of as solid are boiled away into a gas. The model suggested that the upper atmosphere could be saturated with gaseous sodium and potassium. These elements are known to be incredibly efficient light absorbers, their atoms hungry for photons across a wide spectrum. Deeper down in the crushing pressure of the lower atmosphere, even more exotic materials could be vaporized. Titanium oxide, the same compound used to create brilliant white paint on Earth, would at these temperatures form a hazy vapor that swallows light. Vanadium oxide could do the same. You would not see clouds of water ice or condensed vapor as we know them. You would see shimmering, ever-present fogs of vaporized metal. It's a vision straight from a blacksmith's forge, a sky woven from the very stuff of rock and dust, superheated into a light-eating miasma. Under the relentless glare of its parent star, this metallic haze would act like a planetary welding goggle, absorbing the vast majority of incoming energy before it could ever reach a surface that may not even be solid. The faint glow of the world would be the heat of this celestial furnace, a dull infrared blush radiating from an atmosphere that has turned itself into a planetary heating element. The air itself would be a form of molten rock, a shimmering gaseous ore that denies the existence of day. The very concept of a clear sky would be meaningless here. There's only the deep oppressive and everlasting gloom of a metallic twilight, a permanent state of dusk created not by the setting of its sun but by a sky that refuses to let the sunlight in. This planet's atmosphere would be a shroud of incandescent metal, a cosmic paradox where the brightest elements forge the deepest darkness. But another, perhaps even more profound possibility lurked within the spectral data. The broad absorption features also hinted at the presence of complex molecules, specifically carbon-based chains. On moons like Saturn's Titan, the sun's ultraviolet radiation strikes methane in the upper atmosphere, breaking it apart and allowing it to reform into heavier, more complex organic molecules. This process creates a thick orange-brown haze of what we call tholins, a sticky, tar-like organic soot that coats Titan's surface. Now imagine that process amplified on a planetary scale, supercharged by a star far hotter and more intense than our own. On this world, the sheer energy pouring into the atmosphere could be driving a runaway production of these complex organic compounds. We wouldn't be seeing a thin orange haze. We would be witnessing an atmosphere choked with a dense planet-wide layer of primordial soot. It would be a sky saturated with the very building blocks of life, but twisted into a form that creates an all-encompassing darkness. Think of it as a world perpetually shrouded in the smoke of its own creation. Every photon of starlight that enters this atmosphere risks collision with one of these tangled long-chain hydrocarbon molecules. The light's energy is absorbed, converted into vibrations, and heat its journey ending just a few hundred kilometers into its descent. The result would be a deep brownish-black sky, an endless canopy of organic smog that traps both light and heat with terrifying efficiency. Beneath this oppressive ceiling, the temperatures would soar to unimaginable levels, creating a pressure cooker environment, where even more complex chemistry could take place. This hypothesis carries a haunting poetry. The very elements that on Earth led to the flourishing of life could here be responsible for creating one of the most inhospitable environments in the known universe. It's a stark reminder that chemistry is ambivalent to our hopes. In this cauldron, the ingredients for life have not cooked up a cradle but a tomb. A dark, sterile, superheated prison where the sky itself is an impenetrable barrier made of the stuff of life yet utterly devoid of it. The darkness here is organic, a shadow born from the same carbon that forms our own bodies. Yet there remained a third, even more exotic interpretation of the smeared spectrum, a possibility that pushes the boundaries of our understanding of matter itself. This hypothesis suggests that we are not looking at a gas at all, but at something far stranger. On any planet, as you descend through the atmosphere, the pressure and temperature increase dramatically. If the conditions are just right, you can reach a point known as the critical point. Beyond this threshold, the distinction between liquid and gas dissolves. Matter enters a fourth state, a supercritical fluid. A supercritical fluid has the density of a liquid, but flows with the viscosity of a gas. It is a turbulent, roiling, high-pressure medium with bizarre and powerful properties. On Earth, we use supercritical carbon dioxide to decaffeinate coffee beans. It's a potent solvent that can penetrate solids like a gas. On this alien world, the entire lower atmosphere, a layer potentially thousands of kilometers thick, might exist as a permanent ocean of supercritical hydrogen or helium. To incoming starlight, such a medium would be utterly confounding. It wouldn't be transparent like a gas, nor reflective like a liquid surface. A supercritical fluid is so dense and its molecules are packed so tightly that it can bend, trap and absorb photons in ways that defy simple categorization. Light entering this layer would be like a swimmer entering a pool of thick honey. Its path would be bent, its energy absorbed, its progress relentlessly halted. The fluid would churn with colossal convection currents, creating a chaotic, pressure-driven weather system on a scale we can barely comprehend. This isn't a sky. It's a bottomless, planet-sized pressure vessel. There would be no surface to stand on, just a gradual, unending descent into a darker, hotter and denser state. To journey into this world would be to sink through an endless sea of something that is neither air nor water, a medium where the very laws of optics break down. The light from its star is not just blocked. It is captured, drowned and pressurized out of existence in a planetary ocean of supercritical fluid. The darkness of this world then would be the darkness of the deepest abyssal trench, extended to encompass an entire globe. So we stand at a profound turning point. The enigma of the pitch-black planet is no longer a geological puzzle. It is an atmospheric one. The culprit is not the ground, but the sky. Whether it is a celestial forge shimmering with metallic vapours, a chemical factory choked with organic soot, or a bizarre ocean of supercritical fluid, the conclusion is the same: this world has perfected the art of atmospheric absorption. It is a natural-born black body, a planet whose very essence is defined by its ability to make light disappear. We have peeled back the first layer of this incredible mystery, only to find a mechanism of darkness far more complex and beautiful than we could have ever predicted. The question of what makes the planet dark now has a set of viable, if mind-bending, answers. But this revelation only serves to create a new, more urgent question, a question that pushes us forward into the next stage of our investigation. We may have an idea of the chemical recipe for this darkness, but what about the architect? What cosmic chef, what unique combination of stellar and planetary evolution could possibly cook up such a brew? Why here? Why this planet orbiting this particular star? What extraordinary circumstances could have conspired to create not just a dark world, but a world whose very atmosphere has become a symphony of shadows? The chemistry is only half the story. To truly understand this place, we must now investigate its history, its violent birth, and its relationship with the star that it so perfectly defies. So we have found the culprit, we have identified the light thieves, that impossibly dense atmospheric shroud saturated with vaporized sodium, potassium, and perhaps even exotic titanium oxides serves as this world's cosmic velvet cloak. It is a chemical trap, a molecular labyrinth where photons check in but they never check out. The how of the darkness is beginning to yield its secrets. Yet in pulling back this one layer of the mystery, we have exposed a far more formidable and terrifying question. In swallowing 99% of its star's relentless energy, where does it all go? You cannot simply delete that much power from the universe. Energy as fundamental as existence itself must be conserved. It changes form, it moves, it transforms, but it never ever vanishes. This planet is a black box, and inside it a thermal engine of unimaginable violence is roaring to life. The light it devours is reborn as something else entirely. It is reborn as heat. Imagine standing on a world where the sun never sets, a place tidally locked to its parent star, one hemisphere trapped in perpetual blistering day, the other in an eternal frozen night. On the day side of this pitch-black planet, the sheer influx of energy is staggering, an unending torrent of radiation that dwarfs anything in our own solar system. This is not gentle warmth. This is a celestial blowtorch, a constant focused blast furnace operating on a planetary scale. The upper atmosphere, that light-devouring haze we've just unmasked, becomes the front line of this assault. It is here that the energy is first processed and the consequences are nothing short of cataclysmic. Molecules are not merely warmed, they are torn apart. The intense radiation likely triggers widespread thermal dissociation, ripping complex compounds into their constituent atoms and creating a superheated, chemically reactive plasma at the edge of space. This upper layer becomes a kind of planetary shield, but one that glows invisibly in the infrared, a seething cauldron of dissociated gases at thousands of degrees. It's the lid on a pressure cooker of cosmic proportions, but this lid is absorbing more and more heat every single second. Underneath it, deeper in the atmosphere, the pressure builds to crushing levels hundreds, maybe thousands of times that of Earth's. Here, the absorbed energy saturates the thick, soupy air, turning it into a uniform supercritical fluid. The very distinction between gas and liquid begins to blur into a singular oppressive medium. So how does a planet cope with such an inferno? On Earth, or even on gas giants like Jupiter, excess heat is eventually radiated back into space. It's a balanced budget of energy in and energy out. This world, however, has a broken thermostat. Its atmosphere is so profoundly opaque that radiating heat away is astonishingly inefficient. It is designed to trap energy, not release it. The planet is left with only one viable option for survival, one terrifyingly powerful mechanism to keep from boiling itself into oblivion: convection. But this is not the gentle rising of the warm air that creates fluffy cumulus clouds in our skies. This is convection on a monstrous planetary scale. Colossal plumes of superheated gas energized in the depths must erupt upwards with explosive force like magma from a volcano. These are not weather systems, they are atmospheric eruptions. Imagine towers of roiling incandescent gas wider than continents punching through the upper haze. They carry the thermal payload from the crushing depths to the tenuous upper layers, great conveyor belts of raw heat. This process would create a sky in constant violent turmoil. An observer floating in this atmosphere, an impossible thought, would see not clouds, but glowing ascending blobs of plasma-like gas, a celestial lava lamp powered by a star. Yet this vertical movement is only half of the story. The planet's tidally locked nature creates the most extreme temperature gradient imaginable in the known universe. On one side you have the day-side furnace. On the other, the night side, a realm of absolute cold forever shielded from the stars' gaze, a place where temperatures plummet to hundreds of degrees below zero. This differential is the engine. It is the driving force behind winds that would make the most powerful hurricane on Earth seem like a gentle breeze. The superheated gas, having risen on the day side, has nowhere to go but sideways. It spills over a tidal wave of scorching air flowing from the point directly beneath the star towards the terminator, the twilight zone that separates eternal day from endless night. Our atmospheric models, the elegant computer simulations that predict weather on Earth and map the belts of Jupiter, simply break down here. They are not built for this kind of punishment. They predict wind speeds not in hundreds, but in thousands of miles per hour. We are talking about supersonic jet streams that circle the entire planet rivers of fire, carving a path through the upper atmosphere. These winds would be so far so powerful that they would likely generate immense electrical fields through friction, sparking lightning storms that are not flashes of light, but continuous glowing sheets of plasma that stretch for thousands of miles. The sound would be a constant planet-circling sonic boom, a scream so loud and low, it would be felt as a vibration in your very bones. This is not weather. This is a planetary energy crisis playing out in real time. It is a world desperately trying to share its unbearable thermal burden. As this supersonic flow of superheated gas screams across the terminator into the frozen abyss of the night side, it undergoes a transformation that is as violent as its creation. The sudden, shocking drop in temperature forces the exotic elements within the atmosphere to change state. It forces them to condense. What was a searing hot vapor on the day side becomes a liquid and then a solid on the night side. We must abandon all terrestrial comparisons here. This is not a gentle rain of water. This would be a torrential downpour of molten metal. Imagine a sky weeping droplets of liquid iron, or perhaps a black greasy snow of condensed carbon soot falling through the darkness. Depending on the precise chemistry, we could be looking at sodium blizzards or clouds that rain molten glass sideways in the supersonic winds. This is a cryoforge where the ingredients cooked in the dayside furnace are flash frozen and dropped into the perpetual gloom below. This process of condensation releases even more energy into the nightside atmosphere, what scientists call latent heat, which slightly warms the upper layers before the material rains out. This creates bizarre thermal inversions where the air gets warmer the higher you go before plunging into the extreme cold of space. The nightside isn't a quiet, static place. It's a dynamic dumping ground, a place of constant exotic precipitation, where mountains of metallic or carbonaceous material might be accumulating on the surface over billions of years. The sheer weight of the atmosphere would mean this rain falls incredibly slowly, a lazy, glittering drizzle of death that could take weeks to reach the unseen surface. The pressure differential between the hot expanding dayside and the cold contracting nightside is the primary engine of this entire system. It's a far simpler atmospheric machine than Earth's, which is complicated by rotation, oceans and seasons. This is a brute force system, heat here, cold there. The result is a singular massive circulation cell that wraps the entire planet. One giant roaring river of air flowing from light into darkness. This monstrous cycle has profound implications for the planet's structure. Our model suggests the atmosphere couldn't possibly be uniform. It must be stratified into distinct hostile layers. Deep down, near what we presume is a surface, the immense pressure and relatively stable temperatures might create a stagnant, almost solid layer of atmosphere, a region where gas is compressed to the density of a liquid. Nothing moves here. This is the calm at the heart of the storm, a place of eternal crushing stillness. Above this dead zone would be the convective layer, the troposphere of this alien world. This is the battlefield we've been exploring, a domain of violent updrafts, supersonic winds and metallic rain. It is the planet's circulatory system pumping heat from the heart on the day side to the cold extremities of the night side. Higher still, we would find the stratosphere, the superheated lid where the star's energy is first absorbed. This layer cooked by radiation from above, and the violent convection from below would be a chemical hellscape of dissociated atoms and bizarre short-lived molecules that can only exist at such extreme temperatures. And finally, at the very edge of the world is the exosphere, the wispy, tenuous outer layer. But here it wouldn't be a gentle fade into the vacuum of space. The intense stellar radiation and the sheer energy of the planet's atmosphere would be blasting it away, creating a colossal comet-like tail of escaping gas that follows the planet in its orbit. This world is not just black. It is bleeding its very substance into space, a slow, inexorable evaporation under the glare of its sun. The very concept of a planetary energy budget, a cornerstone of climatology, must be rewritten for a world like this. Planets in our solar system exist in a state of near equilibrium. They radiate away almost as much energy as they receive. This planet does not. It is an energy hoarder. It absorbs and absorbs, and the internal machinery required to process that energy has reached a level of violence that defies our experience. It challenges the very definition of a planet's atmosphere, blurring the line between meteorology and high-energy physics. We are not just looking at a weather system. We are looking at a planetary-scale heat engine operating at the limits of stability. Every model we create, every simulation we run, pushes our computers to their breaking point. They hint at feedback loops and resonant frequencies in the atmospheric flow that could cause the entire system to oscillate to pulse. The planet's weather might not be just violent. It could be wildly unpredictable, with periods of relative calm shattered by globe-spanning storms of unimaginable fury. We have peered into the workings of the sky. We have traced the path of stolen energy as it is transmuted into wind and supersonic chaos. We have imagined the strange, terrible rains that fall in the eternal darkness. We have built a new, terrifying picture of this world's atmosphere, a system that stretches our science to its absolute limits. But in doing so, we have completely and utterly ignored the one thing that lies beneath it all. We have treated this planet as a ball of gas, a problem of thermodynamics alone. But somewhere buried deep beneath the crushing pressure, the metallic snows, and the endless violent winds, there must be a surface. There must be solid ground. What kind of geological stage could possibly host this celestial pandemonium? What kind of planetary crust could survive and evolve under the constant bombardment of a sky that is actively trying to boil, blast, and bury it? The inferno above is only half the story. To truly understand this pitch-black world, we must now descend. We must journey through the storm and ask the final terrifying question: what lies at the bottom? And so, with that last ghost of a signal, that faint spectral fingerprint of vaporized titanium and vanadium oxide, the final piece of the puzzle clicked into place. It was a clue so unexpected, so contrary to our models of planetary atmospheres, that it forced us to discard everything we thought we knew. The darkness of this world wasn't a simple coat of paint, a mere surface feature. It was the result of a vast planet-spanning engine, an intricate piece of celestial machinery operating on principles of physics and chemistry, pushed to their most terrifying extremes. To understand this pitch-black planet, you have to stop thinking of its atmosphere as a mere blanket of gas. You must see it for what it truly is: a velvet prison for light, a multi-layered trap so perfectly engineered that for a photon entry is a death sentence. The emerging scientific consensus, a picture painstakingly assembled from scattered photons and gravitational wobbles, reveals not a single cause, but a cascade of 3 interlocking mechanisms. Each is formidable on its own, but together they form an alliance of physics that strips the very energy from starlight transforming this world into a cosmic ghost. We have come to call this trifecta the soot of worlds, the labyrinth of pressure, and the heart of oblivion. It begins high above the planet's unseen core in the tenuous upper reaches of the thermosphere, where the boundary between planet and raw space begins to blur. Here, under the unrelenting glare of its parent star, a form of alien alchemy is at work. The star's radiation, a torrent of high-energy particles and ultraviolet light, acts as a celestial blowtorch searing the top of the atmosphere. Simple molecules are torn apart, their constituent atoms ionized and sent careening through the thermosphere. But this isn't just destruction, it is creation. In this violent, superheated crucible, atoms of sodium, potassium, and even heavier elements like titanium, once locked away deep inside the planet's core and dredged up by unimaginable convection currents, are forged into something new. They don't form a simple gas. Instead, they begin to nucleate, creating microscopic grains of what can only be described as an exotic metallic smoke. This is the soot of worlds. Imagine a fog, not of water droplets, but of atom-thick flakes of metal and mineral, each particle exquisitely shaped by chemistry we are only beginning to comprehend. These are not the reflective crystals of ice you might find in the clouds of Jupiter or Saturn. They are the antithesis of reflection. Their quantum structure is tuned to capture the energy of an incoming photon and convert it into a shudder of vibration, a minuscule increase in its own heat. It's a haze of pure absorption, a shroud of darkness woven from the planet's own vaporized essence. Light from the nearby star arriving after its journey across millions of kilometers strikes this initial layer. A staggering amount, perhaps 30 or 40% of the total light, perishes right here. It doesn't bounce off, it has simply consumed its energy, bled away to further heat this already infernal smokescreen. For any photon that survives this first trial, its journey has only just begun. It now plunges deeper past the shroud of metallic soot, and into the second mechanism, the labyrinth of pressure. This is where the sheer scale of the planet's atmosphere becomes a weapon against light. The density and pressure increase exponentially with every kilometre of descent. We are no longer dealing with a gas in the terrestrial sense, but a thick, oppressive medium, hundreds of times denser than the air you're breathing now. And it is in this crushing pressure cooker that a phenomenon known as Rayleigh scattering, the very same process that makes our own sky blue, is twisted into a sinister new form. On Earth, sunlight scatters off nitrogen and oxygen molecules, with blue light scattering most effectively, painting our sky in its familiar hue. But here, in an atmosphere choked with heavy metallic vapours under immense pressure, the scattering becomes something else entirely. It becomes a gravitational gyroscope spinning light away from its intended path. A photon travelling in a straight line strikes a molecule of vaporized sodium. Instead of being absorbed, it is deflected, sent careening off at a new angle. But crucially, because of the incredible density gradient, the path of least resistance is not back up towards the vacuum of space. It is sideways or even further down into the ever-thickening gloom. The photon is now a prisoner. It ricochets from one molecule to the next 1 billion times a second, trapped in a planetary pinball machine from which there is no escape. Each collision, each minute transfer of energy robs the photon of its momentum. Its wavelength is stretched, its power sapped. It is a slow, agonizing death by 1,000 cuts. A beam of brilliant starlight containing the entire spectrum of colours is dismembered. It is scattered and rescattered, its journey transformed from a straight vector into a chaotic random walk, a spiral that leads ever downward deeper and deeper into the planet's gravitational well. The atmosphere itself has become a light trap, a one-way membrane. Light can pour in, but the tortured randomized path it is forced to take on the inside ensures it can never find its way back out. The energy remains, but it is no longer light. It has been converted through this brutal process of thermalization into the one thing this world has in abundance: heat. This process alone, this combination of a light-absorbing aerosol and a light-trapping pressure gradient, would be enough to create a remarkably dark world. It would explain an absorption of 90, perhaps even 95% of all incoming light. But the data, the stark reality of the transit observations, tells us the number is closer to 99%. There is almost nothing left. The darkness we observe is too profound, too absolute, for even these two powerful mechanisms. To account for that missing few percent, we have to venture into the planet's deepest, most hidden layer, a region so alien that our laws of physics begin to fray at the edges. We must descend into the heart of oblivion. Imagine pushing down thousands of kilometers below the cloud tops through the metallic haze and the oppressive labyrinth of gas. The temperature now surpasses that of molten rock, and the pressure is millions of times that of Earth's sea level. Here matter can no longer exist in any state familiar to us. It is not solid, it is not liquid, it is not gas. The distinction between these phases has been annihilated by the sheer violence of the environment. The atmosphere now composed of vaporized silicates and ion transitions into a supercritical fluid. It's a bizarre halfway state of matter flowing like a liquid, but with the density of a solid filling its container like a gas. There is no surface. There is no boundary. There is only a seamless, terrifying gradient into the planet's core. And this supercritical fluid of molten rock and metal has an optical property that serves as the final seal on the photon's tomb. It does not scatter light. It does not reflect light. Its very quantum nature, its electron shell structure warped by the unbelievable pressures, is to simply absorb. Any weary photon that has miraculously survived the gauntlet of the upper layers, that has navigated the labyrinth, and still possesses some vestige of its energy, meets its final unceremonious end here. It plunges into this sea of quasi-liquid rock and is extinguished instantly, its energy assimilated into the churning convective fluid with perfect efficiency. This is the final destination, the point of no return. It's the reason why the planet's albedo, its reflectivity, is statistically indistinguishable from zero. No light that enters the deep atmosphere ever emerges, so we can now see the whole horrifyingly beautiful picture. It is a symphony of darkness played in 3 movements. The starlight first encounters a high-altitude smokescreen of metallic soot, which kills a significant portion of the light on arrival. The survivors then plunge into a deep, impossibly dense atmosphere that acts as a physical maze, scattering the light inward and downward, never outward, slowly bleeding it of its energy and converting it to heat. And finally, any photon that manages to penetrate to the lowest depths is executed by a bizarre ocean of supercritical fluid, a state of matter that is the physical embodiment of a black hole's event horizon in atmospheric form. This world did not simply form this way by accident. We are witnessing a state of extreme planetary evolution. Tidally locked to its star, one side is trapped in eternal day, the other in eternal night. The day side, perpetually baked by its sun, has had its very surface and crust vaporized over billions of years, creating the raw materials for this light-eating atmosphere. The immense heat drives the powerful convection currents that dredge exotic materials from the mantle, and feed the alchemical forge in the upper atmosphere. The planet is not just dark. It has actively engineered its own darkness. It has become the ultimate energy collector. While other planets reflect a significant portion of their star's energy back into space, this world keeps it all. It has become a perfect thermodynamic engine, a cosmic furnace that has learned how to consume every last joule of energy it receives. The blackness is not a void. It is a presence. It is the manifestation of a billion-year-long process, a testament to the fact that in the galactic wilderness, chemistry and physics can conspire to produce architectures of matter more extreme and more efficient than anything we could have ever conceived. We set out searching for a dark planet, thinking we might find a world coated in a simple, light-absorbing chemical. Instead, we have found a world that has weaponized its own atmosphere, turning it into a labyrinthine prison for energy. We have found a world whose very fabric has been recoded by its star, a monument to the staggering, often terrifying diversity of worlds that populate the cosmic ocean. It is a masterpiece of alien engineering forged by nature itself. We have solved the mystery of how it is so dark, but in doing so, we have opened a door to a much more profound and unsettling question. In a universe filled with billions of planets, how many more of these pitch-black furnaces are out there, silently hoarding the energy of their stars, waiting in the everlasting darkness? And so the model holds. The simulations, the spectral analyses, the agonizing years of deciphering the faintest of signals, all converge on one inescapable truth. Before us lies a world that has mastered the art of disappearance, a planet that has swallowed the dictionary of light and left us with a single, deafeningly silent word: darkness. The journey to this point of understanding has been a descent, a cautious intellectual spelunking into a cave of cosmic impossibility. We began with a flicker, a statistical ghost haunting the data, a star that seemed to dim just a little too much, a little too strangely. From that faint whisper, we followed a trail of breadcrumbs scattered across light years, each one leading us deeper into a mystery that defied our neat categories and comfortable assumptions. We have now arrived at the bottom of that abyss, and looking up from this new profound depth, the universe we thought we knew appears irrevocably changed. For the longest time, our search for other worlds was in truth a search for ourselves. We looked for terrestrial planets, for ocean worlds, for gas giants that rhymed with our own Jupiter or Saturn. We built our expectations on the architecture of our solar system, a familiar blueprint that we projected onto the cosmos. Planets in our imagination were meant to be reflectors. They were celestial canvases upon which a parent star would paint its brilliance, creating palettes of swirling clouds, ochre deserts, or azure oceans. They were partners in a dance of light. But this pitch-black world does not dance. It stands implacable and absolute, a void that consumes the energy of its star with an efficiency that borders on the theoretical. It is not a partner, it is a singularity of shadow. This discovery is more than just the addition of a new exotic specimen to our celestial zoo. It is a fundamental paradigm shift, a quiet but seismic event that has cracked the very foundations of planetary science. We are forced to confront the humbling reality that our definition of normal was never a universal law. It was merely a local ordinance, a byproduct of our single lucky data point in the cosmos, our own solar system. Think of every model we have ever built, every assumption about how an atmosphere must behave to be stable, how it must reflect and radiate heat to maintain equilibrium. This world violates the spirit, if not the letter, of those laws. It shows us that a planet can exist in a state of perpetual extreme energy absorption, creating a thermal and chemical environment so alien that our vocabulary struggles to describe it. We are like ancient cartographers who, after a lifetime of drawing maps of their own continent, are suddenly presented with proof of another unimaginably different landmass across the ocean. The existence of that new land doesn't just add to the map, it forces a re-evaluation of the entire globe. It shatters the arrogance of thinking your own home is the full measure of the world. This planet is our new continent. It is the terra incognita of planetary evolution, and its discovery demands that we redraw the boundaries of possibility. Where we once drew a line, we must now sketch a vast, unexplored territory. The assumptions we held so dear about the necessary reflectivity of clouds, about the balance of energy budgets, about the very colours a world could be, have been exposed as provincialisms. The implications ripple outwards, touching every facet of our search for life. For decades, the hunt for habitable worlds has been guided by the principle of the Goldilocks zone, that narrow temperate band around a star where liquid water might exist. We searched for pale blue dots for worlds that resembled our own. But this dark sphere teaches us a harsh and exhilarating lesson. The universe is far more creative, and perhaps far more perverse, than we have ever given it credit for. It can forge worlds in fire and shadow that operate on principles we're only just beginning to grasp. What other chemistries might thrive in an atmosphere of vaporized rock and exotic metals? What form of energy exchange could occur on a surface perpetually blasted by its star yet shrouded in an almost perfect light-absorbing blanket? The planet is almost certainly lifeless as we understand the term a raging furnace world of unimaginable torment. Yet its existence shatters our complacency. It forces us to ask more daring questions. If a world can be this extreme in its physics, what extremes of biology might be possible elsewhere? If the universe can build a planet that is 99% black, what other seemingly impossible architectures has it constructed in the unseen corners of the galaxy? We have been searching for reflections of Earth, and in doing so we may have been blind to the true staggering diversity of creation that lay waiting in the shadows. This world is a cosmic wake-up call, a reminder that to find the truly alien we must first be willing to abandon our preconceived notions of what a world is supposed to look like. We must learn to search, not just for the familiar glint of a distant ocean, but for the profound and telling signature of an absolute and perfect void. This newfound awareness fundamentally retools the mission of the next generation of astronomers. The hunt is no longer just about finding another Earth. It is now also about finding the anti-Earths, the outliers, the freaks of cosmic nature that push our theories to their breaking point. Telescopes of the future instruments of breathtaking power and sensitivity will be programmed with new eyes. Their algorithms will be taught to look for this specific signature of profound darkness, to flag the impossibly deep transits that other systems might have dismissed as instrumental error or statistical noise. We are now actively hunting for ghosts. We are looking for the holes in the sky, for the telltale signs of planets that have mastered the art of camouflage by embracing utter blackness. Each new candidate will be another piece of the puzzle, another stress test for our models. Perhaps we'll find that these pitch-black worlds are a common phase in planetary evolution, a temporary state for gas giants as they migrate perilously close to their stars. Or perhaps they are genuine rarities, the products of a perfect storm of unique elemental compositions and orbital dynamics, making each one a priceless cosmic artifact. The search will require a new kind of patience, a new kind of insight. We will be sifting through the noise of the cosmos not for a signal but for a profound and structured silence. We will be listening for the sound of light being extinguished. This is the new frontier, the exploration of cosmic extremes. We will seek out the hottest planets, the coldest rogue worlds wandering interstellar space, the planets with atmospheres of diamond and oceans of methane. And among them we will seek their darkest brethren, these velvet traps for starlight that hold the most extreme secrets of planetary formation. The study of such a bizarre and hostile place might seem at first glance to be a purely academic exercise, a fascinating but ultimately distant curiosity. But the truth is far more intimate, far more relevant to our own existence here on Earth. Every law of physics, every chemical reaction that governs our own blue marble is being tested in that distant crucible. This pitch-black planet is not operating on alien physics. It is a product of the very same universal statutes that allow you to feel the warmth of the sun on your skin. What it provides is a laboratory at the edge of creation, a place where those laws are pushed to an almost unimaginable extreme. By studying how its superheated atmosphere of sodium and potassium vapor absorbs light with such terrifying efficiency, we gain a deeper, more nuanced understanding of the quantum mechanics of atoms and molecules. These are the same mechanics that drive the greenhouse effect in our own atmosphere, that govern the way sunlight is absorbed by our oceans and reflected by our ice caps. To understand why that world is black is to understand with greater precision than ever before why our world is blue, why Mars is red, and why Venus is a brilliant blinding white. The universe, in its infinite generosity, has provided us with a control group of the most extreme kind. By observing how matter and energy behave under conditions we could never hope to replicate on Earth, we refine the fundamental theories that are the bedrock of all science. The light from that distant star after its long journey across the expanse does not just tell us about a strange dark world. It carries an echo, a deeper truth about the universal nature of matter, a lesson in physics that is as applicable in a laboratory here on Earth as it is in the raging black stratosphere of a planet trillions of miles away. And so we find ourselves at the end of this particular thread of inquiry, but at the beginning of 1,000 others. We are left with a new and powerful sense of perspective. For millennia we have looked up at the night sky and seen it as a canvas of brilliant shining lights against a static empty backdrop. We saw the stars, the galaxies, the nebulae, all of them glorious emitters of energy. But we are now learning to see the darkness as well. Not as an absence, not as a void, but as a dynamic and vital component of the cosmos. The darkness can hold worlds, it can harbour secrets, it can be a destination. The existence of a pitch-black planet, a world that has chosen to cloak itself in shadow, is a profound statement from the universe. It tells us that the most incredible wonders may not be the ones that shine the brightest, but the ones that hide in plain sight, their nature concealed by a perfect and deliberate rejection of the light. It reminds us that for all we have discovered, for all the breathtaking images captured by our telescopes, we have only just begun to scratch the surface. We are still children paddling in the shoreline of a vast cosmic ocean, and we have just found a shell of a colour we never knew could exist. What other impossible colours, what other unimaginable forms await us in the deep? Our journey to this one world of eternal night is over, but the larger human journey into the great, beautiful and often terrifying unknown has been forever expanded by its discovery. The search continues now with a new awareness, a new humility and a new burning question. What else is hiding in the dark? The universe is waiting for us to find out. It has set the stage with wonders beyond our imagining, and our purpose is simply to keep looking up and to dare to see what is truly there.